Recording with audio. Excellent. So who is ready for the exam on Monday? Who has any questions from the homework? Okay, let's start there. 29. Estimate how long it would take one person to mow a football field using an ordinary home lawn mower. Push mower. State your assumptions, such as the mower moves with 1 kilometer per hour and has a half-meter width. Okay. Well, who knows the dimensions of a football field? 100 yards long by how wide? 50 yards wide? Okay. You did? With a push mower? Ow. Why? Okay. All right. Well, what's the first thing we got to do? Convert it to meters. So how do we convert 100 yards to meters? I don't know. But I do know that somewhere on your index card should be 2.54 centimeters is defined as 1 inch. Okay. Well, let's see. We've got 100 yards, and there are 36 inches in 1 yard, right? So we're going to go with inches on the top and yards on the bottom, so they cancel. And there are 36 of them in every 1 yard. So we've got the length in inches. Now what do we do? Going from inches to centimeters. So which one do I write where? Centimeters above, inches below, and we know that there's 1 inch for every 2.54 centimeters. So we've got the 100 yards into centimeters. Inches have canceled. And now we need to turn those centimeters into meters. So we're going to have a number in units. What do I write? Say again? Okay, which one do I put on top and bottom? Meters on the top, centimeters on the bottom, so they cancel. 1 meter for every 100 centimeters. And that gives us the length of a football field in meters. Break out your calculators. Did anyone else get anything differently? Now, we're assuming that that is a precise number, that 100 yards. which means if we assume that 100 yards is a precise number, not a measurement, but a definition, because football fields are defined as 100 yards long. And the rest of these are all definitions. We can conclude then that this is a precise number. What else can we tell? Well, we can tell that the width is half of that, but more specifically, we can say we've got 50 yards that we're going to multiply by a conversion of, we want it to end up in meters, and we've got it in yards. What numbers do I put here now? Exactly. We've got 100 yards is equal to 91. 91.44 meters. So we take 50 yards, multiply by 91.44, and then divide by 100, and we get the width of the football field as meters. And again, we're still dealing with definitions, not measurements. So we can still keep this as a precise number. Okay. Now you've got to make a decision. Are you going to mow it across, back and forth, the narrow way, or are you going to mow it the long way? You're going to mow the same amount of area either way, but what are our assumptions, Kennedy? How much? 1 kilometer per hour. And it's 0.5 meters wide. Okay. We need that kilometers per hour in meters per hour, right? So if we have 1 kilometer per hour, what do we multiply? What conversion do we use to turn it into meters per hour? 1,000 what? Okay, so I put kilometer here, and I put meter here. Okay, that cancels out the kilometers. So I put 1 kilometer per 1,000 meters. And that gives us, that's pretty easy arithmetic, even I can do that, 1,000 meters per hour. Okay. So how many hours does it take me to mow 91.44 meters? .44 meters times what? I want hours left over, right? Well, I've got meters per hour, but I want to eliminate meters, and I want to keep hours. So if I'm going 1,000 meters in 1 hour, put the 1,000 meters per 1 hour right here, and that means it takes me how many hours to mow the length of the football field once? Okay, what would that be in power of 10 notation? 9.144 negative 2, right? Times 10 to the negative 2 hours. Is that somebody's phone? Okay. That's how long it takes to make one pass. How many passes is it going to take to mow the whole field? You got this width to cover, and you're going to cover 1/2 of a meter for every pass. So let's do that. What's that number? 45.92? 0.72. 45.72 meters wide. And you're going to convert that with what? You want to know how many passes, right? So put passes on top, meters on the bottom. Meters cancel. And you cover how many meters per pass? So you've got 0.5 per pass. That means it's going to take 91.44 passes to cover the width. And it's going to take 9.144 times 10 to the minus 2 hours for every pass, right? And that's what we want. Our estimation should be how long is it going to take to mow with this push mower? So, we've got this is hours per pass, right? This is how long it takes to do one pass. So we take our 91.44 passes and we multiply by hours per pass. So those cancel. And we know we've got 9.144 times 10 to the minus 2 hours for every pass. .4 hours. Yeah. I don't either. But it's an estimate, right? Is anything we did there wrong? No. But if you're just estimating, how can it be wrong? You work the problem like this, I am not going to count it wrong. Okay? But how might we make this a lot faster? If we were just going to estimate. Ugh. Did anyone else come in besides Alexia? Since I handed out homework? How might, seriously, somebody come up with an answer. How might we make this estimation more quickly? Well, give me a minute while I... There you go, Richard. There you go. Yeah, I know. They in the back of the book they come up with like a couple of hours. Well, if you're limited to, if you're only moving at a 1 kilometer per hour, I stand by this math. This is there's nothing wrong with this estimation, unless it's in the assumptions. Because 1 kilometer per hour is what? Like, that's really, really slow. Yeah, well, it's more like a half a mile per hour. Yeah. All right. What? Yeah. Yeah. That's an incredibly slow pace to move at. But those were our assumptions. I don't know what assumptions they used to come up with 2 hours, but if you do the math correctly, I'm not going to, I'm not going to mark that wrong. So, what are the questions from the homework? You were the one that asked about this one. You had one too, didn't you? Oh, that's cheating. You can't copy off of her. What other questions do we have from the homework or from the chapter in general? Okay, well then let's do some drills. How many significant digits are in that? Somebody else? One, just one. Very good, one. How about that one? 3. How about that one? 4. Why? Because the zeros are not just showing you the position. This would be how many? Just 1. The only point of the zeros here is to show you where the decimal place is. This is how putting it in power of 10 notation will make plain the number of significant digits. In power of 10 notation, how would you write this? 2 times 10 to the minus 3. 1 significant digit. How would you write this one? Times 10 to the power of 0. Exactly. Anything to the power of 0 is 1. Or in this case, you move the decimal place 0 times. But you still have 4 digits. Yep. And the homework should be a pretty good reflection of what you should expect on the exam. So, any more questions from the homework? Have any of you started on this week's homework yet? Any of you close to finished? Number 37. The speed v of an object is given by the equation V equals AT cubed minus BT, where T refers to time. What are the dimensions of A and B? What are the SI units for the constants A and B? Okay, this is a good one. And in fact, we will work that one and 38 as well. So, help me out. Read it back to me. What am I looking for? Okay, is that the right equation? V is a function of T. Okay. First, the dimensional analysis. This is something times T cubed. What is this? Velocity. What are the dimensions of velocity? Length over time. This is T cubed. So these both have to end up as length over time. Well, if I'm eliminating three T's, 3 time factors out of the denominator, and I have to start with 4 of them to have 1 left over. Everyone see how that works? And I need a length in the top. So the dimensions for the coefficient A has to be at length per time to the power of 4. Good? And now we need to know the dimensions of B, which is multiplied by time by just 1 power of time. Well, to have 1 left over in the denominator, I have to start with one more than that, so that's going to be T squared. And I still need my length in the top. Now, if I have T to the L over T to the 4th times T to the cubed times T cubed, that leaves L over T. Don't forget the square brackets because these are dimensions, not units. Here, 1 eliminates 1, so I'm left with L over T. And our units match all the way across. Every term is length over time. And that's part A, correct? Okay, what does B want? They want the SI units. Okay, that means the length is going to be meters. Time is going to be seconds. Okay, what are the MKS units for the A? Nope. Meters per second to the power of 4. Right? What are the units of B? Length over time squared, so it will be meters per second squared tells you that B is what? No. B would be acceleration. Remember? M is position. M per second is velocity. How fast does position change? M over second squared is how fast does the velocity or change. A, it would just be weird. Actually, that would be, what would you call it when acceleration changes? because whatever that's called, A would be however fast that is changing. It would be the acceleration of the acceleration of the acceleration. Or in practice, since we haven't made up a word for that, weird is just as good. Read 38. X refers to what? Okay, X. V is speed. Okay. And a subscript what?
Subscript of 0.
Oh, and the subscript 0 means a quantity at time equals T0. Okay. What are the equations they came up with? Okay, am I getting that right? X equals VT squared plus 2AT. Okay, we've got two more of these, right? V naught T.
Plus 1/2 A times T squared.
AT squared, okay. Is that all of it? Then C. Okay. The way you read that V with the subscript 0 is V naught. Okay. Megan, snuck in on me. Somebody get the sign-in sheet around to everybody, all these latecomers. Who has the sign-in sheet? Yeah, I started one going around. And it made it to the second person and okay. Here you go, Megan. Okay, what is the point of the problem? The problem is to find out which of these are possibly correct, or which of them can we demonstrate or cannot possibly be correct. So let's do some unit analysis. X will have units of meters. Velocity is meters per second. Time squared would be seconds squared. So that would leave this with meters seconds. And this would be meters per second squared times seconds, which would be meters per second. So here we have meters equals meter seconds plus meters per second. Does that at all make any kind of sense? No, the units do not match. This one cannot be correct. This one, we've got meters per second times seconds. which cancel, leaving just meters. And this one we have meters per second squared times seconds squared, which cancel, leaving just meters. So we've got meters equals meters plus meters, which is at least makes sense. So this one is possibly correct. And finally, we have meters equals meters per second times seconds, which cancel, plus meters per second squared times seconds squared, which cancel, leaving meters equals meters plus meters. So again, this one is possible. Now, give you one of Hebert's aphorisms that's not only germane in mathematics, but in life in general. Just because it's not possible for both of you to be right, it is still very possible that you're both wrong. Okay? Do we know which of these is correct? Or if either of them is correct? Don't know that yet. We will in a couple of weeks. But in a couple of weeks we're going to find out that in fact B is correct. C is not correct. But just based on unit analysis, we can't say with one way or the other which is correct or wrong, which is incorrect. All we can say is that A is not possibly correct. B and C could be. Either one of them could be, or maybe both of them are wrong. We don't know. So, everybody's good on how to do unit conversions. If you start with an area that's 100 yards by 50 yards, and you figure out how many passes it's going to take with a half-meter wide push mower, moving at 1 kilometer. Do y'all understand how to go through the steps of doing these conversions? If you need to convert miles per second into, into meters per fortnight. Can you go from miles per hour to furlongs per fortnight? But if you know how many furlongs are in a mile and how many fortnights are in a second, you can get there, right? Okay. What about percentage errors? If we measure we did this in one of the labs when we measured the pendulum swing. Remember, we divided the error from your measurements over more and more periods in order to get the percentage error down. Let's say we're measuring these tiles with a ruler. Okay? And I measure that tile as accurately as I can with that ruler, which will give me a measurement down to 1/10 of an inch. And I measure that tile at 12.15 inches. What does this measurement mean? How certain am I of that measurement? No, go with what I said. Right. That the measurement is somewhere between those two numbers. What is the total maximum possible error there? 0.01. Okay, that's our maximum possible error. What's another name for maximum possible error? Say again? No? It's the word you're going to read in the book. It's what you will hear most often. But when we say uncertainty, that's what we mean. The maximum possible error. So our measurement has an uncertainty of 0.01 inches. What is that as a percentage? Say again? How do you get that? Nope. No, but the way you find out the percentage error, the percentage of uncertainty, or the percentage of error, is you measure the amount of uncertainty, the amount of possible error, divided by the whole measurement. Yeah, no, but we'll get there. No, what I want to know is what is the percentage of error associated with that much uncertainty, or the percentage of uncertainty? So it would be 0.01 divided by 12.15. How much is that? And if you multiply it out by 100 to get it into percentage, it becomes 0.08%, or 0.00, yeah, 8.23 times 10 to the minus 4 is the ratios. All right? Or the relative uncertainty. Point is, that's pretty precise, pretty accurate measurement. We're down to 0.08%. What would that error be? What if I couldn't measure it to that precise? What if I could only measure it to the nearest inch? Now I measure it to 12 inches. But what is my uncertainty now? That means it's closer to 12 inches than it is to 11.5 inches or 12.5 inches. Oh, yeah, you're right. One total. Plus or minus a half an inch. So I have a 1 inch of uncertainty in that 12-inch measurement. Now what's my percent error? Say it 4%? Okay, that's about 4%. How did you get that? Nope. 1 inch of maximum uncertainty divided by 12 inches equals 0.08? Now that's a whole lot more uncertainty. That's a whole lot more potential error. So now I can't make my measurement more precise than that. But what if I've got a long enough ruler that I can measure 10 of these tiles in one measurement? And I measure 10 of them to be um, 130 inches. Now, since I know my error is, this is actually 130.0 inches, which means, never mind, I don't want to go down that road. We're saying that the error is still plus or minus a half an inch. Okay? Which means my uncertainty, because I'm using the same instrument, is still plus or minus 1 inch. I'm not plus or minus 1 inch, it's plus or minus a half an inch, but my uncertainty is the 1 inch. So now, what is my percent uncertainty? It's 1 inch in 130 inches is 0.007 or 0.7%. See, I've now, by measuring 10 tiles at once, the same amount of error that would have been, where did it go? Here. Instead of having that same amount of error associated with just, divided over just one measurement, by measuring 10 of them and dividing the same error over 10 of them, I drastically reduced my percentage error. Right? According to this first measurement, my tiles are 12 inches each. When I measured 10 of them, turns out they're closer to 13 inches each than they are 12 inches each. Okay? This is an experiment I've actually done. I measured with the odometer on my truck the distance from my parking space here to my parking space at home by driving the same exact route every day. Now, when I make the trip one time, that distance is 27.9 miles. Okay? When I measured it 2 days and divided by 2, it was still 27.9 miles each trip. After 3 trips, it was still divided by 3, it still came out to 27.9, but by the time I got up to 5 trips, when I divided by 5, instead of 27.9, it was suddenly 27.92. Now, because I have a digital odometer on my truck, I can't make those fractional measurements between 1/10 of a mile. Okay, it's either 0.1 or 0.2 or 0.0. It's never going to be 0.15. But by making the same measurement multiple times and then dividing it, I reduced that error and got a more precise measurement. This is what we did in the pendulum lab. Instead of trying to measure just one period of the pendulum, by measuring 20 periods, you still introduce the same amount of error every time you push that button. But you divide that error over 20 periods instead of just one, and your uncertainty, your maximum error, goes way down. You get a much more precise measurement. Does everyone understand how that worked? And does everyone understand that I might be asking this because it's going to come up on your exam? What more questions does anyone have? Okay. What is the measurement and what is the uncertainty? Oh, don't need the one out of the book. Just make one up. What's the diameter of this beach ball? 11 inches. Okay, so its radius is 10.5 inches. Which, how much uncertainty? Plus or minus 0.05, so 0.1 inch total. All right. That means the radius could possibly be as small as 10.45 inches. And it could be possibly as big as 10.55 inches. That's the range of that measurement. The actual radius is going to be somewhere between these two numbers. When I say plus or minus, let's make that greater, less than, or equal to. Okay? The diameter to 21? Oh, you're right. That should be 5.5. Okay. 21. I told you don't trust me to do arithmetic in my head. Okay, now our radius is right. Okay. Good enough. That's a big beach ball. And I guess not really. That's about the average size of a beach ball. Tells you how much time I spend at the beach. All right. What do we want to know? The uncertainty in the volume or the surface area? Okay. What is the volume of a sphere? Is that correct? It should be inside cover of your book, or front or back, I'm not sure which. Okay. So the minimum that the volume of that sphere could be would be 4/3 pi times 10.45 inches cubed, which works out to somebody got an answer for this one? Yeah. 4,780.1. What's that? Cubic inches? All right. Who's got one for this one? Cubic inches. Okay. What's the difference between these two? Our uncertainty then is 4918.7 minus 4780.1 equals how much? 137.6. Is everybody else getting that same number? That's our total uncertainty. We know that the volume we know the volume to within that much. 138.6? Okay. So what's our percentage uncertainty in the volume of this ball? Right, divided by the median of these two, by the 10.5. Where? 48, 49? I calculated volume based on the measured value. In other words, this number here is equal to 4/3 pi times 10.5 cubed. Okay, who's got the formula for the surface area? Is it 4 pi r squared? All right. Then let's we've got our measured value is somebody call it. Square inches. Okay, that's our measured value. What's the maximum value? And the minimum value? Anybody get different numbers than these? So our maximum error is 26.4 square inches. Say again? That's the surface area of that's based on the measured value. It's actually the median, the midpoint between the maximum and minimum error. And on that note, we're out of time. If any of you have any more questions, if I'm not in class, I'll be in my office. Test is Monday. You've got my email, you got my office phone number. You will notice I have not given any of you my cell phone number or my home number. There's a reason. So don't be shy about using the information I have given you.